Dear students, I am Mahesh Javalkar from Maratha Mandal Polytechnic, and today I want to post a video on objective type of questions, that is MCQ, on digital communication systems. So we will start today digital communication system syllabus. Now if you see the syllabus for the DCET, it is having 7 marks. That means 7 questions can be asked on digital communication. Now in that the syllabus shows that you should know what is analog and digital communication systems. You should know what is baseband, that is basic information signal, and passband, that is when baseband is modulating a carrier you get a passband. So you should know what is baseband and passband. You should know sampling theorem, where the sampling frequency should be greater than or at least equal to twice the highest modulating frequency. Then on the similar basis you should know what is Nyquist criteria and aliasing effect. If you don't follow sampling theorem, if sampling frequency is less than twice the highest modulating frequency, then you will face aliasing effect. Then after that you should know what is quantization, because you have already now studied what is sampling and quantization, so you can convert any analog signal into digital. Okay, that is you can use your PCM, DPCM, DM and ADM types of modulation techniques. Then you should define what is information capacity. Okay, then entropy, bit rate, bits per second, baud rate, symbols per second, and bandwidth of digital data, because it will relate to the channel capacity. Then encoding, some basic modulation techniques which will convert analog to digital, that is pulse code modulation, differential pulse code modulation, delta modulation and adaptive delta modulation. Then you should know what is line coding. Line coding means how do you represent a electrical waveform. How do you represent binary 1 and 0 in that electrical waveform, gives you different types of line coding. Okay, then you have digital modulation techniques, which is an important part. Like in analog modulation techniques you have AM, FM, PM. In digital modulation techniques you can have ASK, FSK, PSK, that is amplitude shift keying, frequency shift keying and phase shift keying. Similarly, after that we'll be studying multiplexing techniques, where we'll be studying frequency division multiplexing, time division multiplexing, and then multiple access techniques, same like multiplexing but the locations will be different, and in that we can get 3 types: time division multiple access, frequency division multiple access and code division multiple access. Then some transmission medias like twisted pair, coaxial cable and optical fibers. So based on this syllabus, what you have already studied in your 4th semester digital communication, you will be getting around 7 questions in your DCET, and all those 7 questions will be based on this portion. So now from here we will start one by one question, and we'll go to the first question, question number 1. Okay, question number 1 says advantages of digital communications are. Options are easy multiplexing, easy processing, reliable, and all the mentioned. Okay, now advantage of digital communications are you can do multiplexing very easily. Multiplexing means combining many signals into one. Okay, that is what a digital multiplexer does. Then you can process it very easily because it is ones and zeros going in the form of electrical voltage, and also it is very reliable as compared to analog. That means the first 3, easy multiplexing, easy processing and reliable, all the above mentioned are the advantages of digital communication. So here the option will be option D. So option D, you can see all the above. Okay, that is easy multiplexing, easy processing and reliable, all will be the advantages of digital communication. Okay, then we'll go to the next question, question number 2. In digital transmission, signal degradation can be removed using what? Okay, now signal degradation means what? Your signal is becoming weak. Okay, signal is becoming weak, and that signal is becoming weak means in digital you are going to represent binary 1 as a pulse and binary 0 as no pulse. Okay, now when you are representing binary 1 as pulse and that amplitude of that pulse is reduced as you are processing, as it is traveling, okay, as the signal is traveling, if the amplitude of the pulse is reduced, then at some stage in between you have to generate that amplitude once more, so that logic 1 remains correct logic 1, it is not deteriorated. Okay, that means you should regenerate the pulse. Okay, that means there is a device called as regenerative repeater, which is option C, which is used when the digital signal is degraded. Okay, So here the option will be option C, a regenerative repeater. Then we'll go to question number 3. What are the disadvantages of digital communication? Disadvantages of digital communication. So here the options are needs more bandwidth, it is more complex, and C is saying it needs more bandwidth and it's more complex, and none of the above mentioned. So here the option C is correct because it requires more bandwidth. As number of bits per second increases, it requires more bandwidth, and to handle that bandwidth the circuit is complex. Okay, so option C will be correct. It needs more bandwidth and is more complex. Okay, then we'll go to question number 4. Analog to digital conversion includes, okay, whenever we do analog to digital conversion, we have to convert analog signal into a sample. Okay, so analog signal into a sample, and that sample has to be quantized to a particular digital value. Okay, so if it is, the sample has to be quantized to a particular digital value. Clear? Now there, first you have to convert samples of analog signal, and then you have to go for quantization. Okay, that means first the analog signal, the continuous wave analog signal will be converted into, okay, so I will show you here. First the analog signal, say this is your analog signal, this will be converted into samples like this. Okay, samples like this, and then every sample, say this is the first sample, if this is say around 2 volts, if this is around 2 volt, this will be represent as 0010. Say this sample is around 3 volt. Okay, so this sample is around 3 volt, this will be represented as 0011. Okay, so in this way, and say again this sample is around 2 volt. Okay, 2 volts, so this will be represented as 0010. So in this way you can represent the analog wave into digital format. So here you can see it is, this is analog wave, this is analog wave, analog, and this whatever you are getting here is digital. Okay, digital. So analog, this first analog wave whatever you have shown here is converted into samples. Okay, is converted into samples. So here you can see the samples. So this analog wave is converted into these samples, and these samples are then converted into binary data here. So here you can see you are going to convert the binary data here. Okay, so samples are converted into binary data, means analog signal is converted into samples, and then they are converted into binary data, means they are quantized. So here the option should be sampling and quantization. Okay, so option C will be there, sampling and quantization. So here you can see there will be option C, sampling and quantization. Then we'll go to the next question, question number 5. The term baseband refers to frequencies representing the information signal such as voice, video, binary data, or all of the above. Now voice also is an information, video can also be information, and binary data can also be information. Clear? So in this case all the first three, voice, video and binary data, all can be the term baseband, which refers to information signal. Clear? Then we'll go to, so here you can see the option of question number 5 is D, all of the above. Then we'll go to next question, question number 6. In passband transmission, the transmission frequency is much greater than message frequency. Okay, now in passband transmission what happens? The baseband signal, the basic information signal, the message signal is going to modulate a carrier, a high frequency carrier, and that modulated carrier will be sent. So automatically the frequency what you're going to send will be higher than the message frequency. Yes or no? So here the option should be true. So here option will be A, true. Then we'll go to the next question, question number 7. Passband transmission is generated using dash process. So obviously we know if you want to increase the frequency, okay, then you're going to involve in a process where baseband signal, that is the basic information signal, is going to modulate a carrier The modulation process can be your ASK, FSK, PSK, anything, but it is going to modulate the carrier and the frequency is going to increase. That means the process used here is modulation. That means here the answer B will be the correct one. Passband transmission is generated using modulation process. Okay. Then we'll go to the next question. The spectrum of the sampled signal may be obtained without overlapping. Without overlapping. Spectrum means a frequency presentation. Okay. Spectrum of sampled signal, signal which is already sampled, okay, will be obtained without overlapping only if you follow the sampling theorem. And the sampling theorem says that sampling frequency Fs should be greater than or equal to twice the highest modulating frequency. So here the option A will be correct. Option A says that Fs is greater than or equal to twice the highest modulating frequency. Clear? Then we'll go to the next question. Question number 9. Which of the following is the process of aliasing? Now in process of aliasing, what happens? Two frequency spectrums will be overlapping because you have not maintained the sampling theorem. The sampling frequency is less than twice the highest modulating frequency. If sampling frequency is less than twice the highest modulating frequency, then you will get spectral overlapping, where the higher information, higher frequency information of the original signal will overlap with the next double sideband lower frequency signals. Okay, then that is called as spectral overlapping. So here the answer will be answer D, spectral overlapping. Okay, next we'll go to the question number 10. The maximum the minimum sampling rate for a signal with 5 kilohertz bandwidth is what? Okay, so here you have to see what are the options given. Now option A is 5 kilohertz, option B is 10 kilohertz, option C is 15 kilohertz, and option D is 20 kilohertz. Okay, so here if you see the frequency what he has given in the question for a signal, so Fm is equal to 5 kilohertz. Fm is equal to 5 kilohertz. Now you want to know what is the minimum sampling theorem. So minimum sampling will be equal to twice into Fm. So this is nothing but twice into 5 kilohertz. This is nothing but 10 kilohertz. So answer has to be 10 kilohertz here. So here the option B will be your answer, and that answer will be 10 kilohertz. Okay, so the minimum sampling rate for a signal with 5 kilohertz bandwidth is 10 kilohertz. Okay, then we'll go to the next question. To recover the sampled baseband signal, dash is used. Okay, now we have seen sampling of low pass signals. Okay, so if you want the basic information signal back from the sampled wave, so you have to use a low pass filter. Only if you use a low pass filter, that is from 0 to Fm, then that basic original signal with bandwidth of Fm will be reconstructed back, will be obtained back. So here the answer should be low pass filter. So to recover the sampled baseband signal, a low pass filter is used. Okay, then we'll go to question number 12. The process of converting the analog sample into discrete form. The process of converting analog sample is already there. Okay, now as I've showed you earlier also, sample will be already there, and if that sample, if you want to convert it into digital value, you have to use levels of quantization, and that is quantization process. Okay, so here the option would be option C, that is quantization. The process of converting the analog sample into discrete form is called as quantization. Then we'll go to the next question. The modulation techniques used to convert analog signal into digital signal. Okay, now these modulations options what they have given is pulse code modulation, delta modulation, adaptive delta modulation. In all these three, we are going to convert analog signal into your binary data. Analog signal will be converted into binary data. That means analog to digital conversion takes place in PCM also, in delta modulation also, in adaptive delta modulation also. In PCM you are going to use sampling and quantization. In delta modulation you are going to use one bit at every sampling time. You are going to convert whether the sampling is above the staircase or below the staircase. You are going to see, and you are going to convert into 1 bit. And modifying delta modulation, you can get adaptive delta modulation also. So there, in all these three, we are going to convert analog signal into digital signal. So the answer should be all the above. Okay, so here you can see the modulation techniques used to convert analog signal into digital signal are PCM, DM, ADM, all the above. All the above. Okay. Then we'll go to question number 14. Channel capacity is equal to, okay, the options are bandwidth of demand, average frequency, noise rate, amount of information per second. Okay, now capacity depends on your bandwidth, and bandwidth depends on information per second. So the last option, that is amount of information per second, is the answer which gives you the channel capacity. That means a channel, how much information per second it can be able to send, or it can be able to travel on that channel, that will give you the channel capacity. How much maximum amount of information. Clear? Then we'll go to the next question, question number 15. Indicate the false statement in order to combat noise. Okay, so which of these four statements are false? So statement A, the channel bandwidth may be increased. B is a redundancy may be used. C is the transmitted power may be increased, and D is the signaling rate may be reduced. Okay, so the channel bandwidth may be increased is a wrong thing, because you cannot increase the channel bandwidth. The channel bandwidth will be specified and it will be given. So here the answer will be answer A. The channel bandwidth may be increased is a false statement. It cannot be increased. It will be specified, and based on that channel bandwidth only you have to determine your data rate. Okay. Then we'll go to question number 16. According to Hartley's law, okay, the maximum rate of information depends on channel bandwidth. The maximum rate of information depends on depth of modulation. A redundancy is essential, or only binary codes may be used. Now if you see Hartley's law, it will give you the channel capacity, which that means channel capacity, that is your rate of information, depends on channel bandwidth. So option A will be correct. The maximum rate of information depends on the channel bandwidth according to Hartley law, because your information rate and channel bandwidth, okay, so that should be matching, then only a proper transmission can take place. Clear? Then we'll go to question number 17. The Shannon-Hartley theorem sets a limit on what? Okay, so the options are highest frequency that may be sent over a given channel, maximum capacity of a channel with a given noise level, maximum number of coding levels in a channel with a given noise level, and option D is maximum number of quantizing levels in a channel of a given bandwidth. Okay, so Shannon-Hartley theorem, if you see, it is C is equal to B into log 2 1 plus S upon N. So that is it is giving you capacity, maximum capacity of a channel with a given noise level. So answer B will be the correct one. It is giving you the maximum capacity of a channel with a given noise level. Clear? Then we will go to the next question, question number 18. To permit the selection of 1 out of 16 equiprobable events, the number of bits required are. Okay, so here the options given are 2, 16, 8 and 4. Options given are 2, 16, 8 and 4. So here if you see, if I show you this working, okay, so options given are 2, 16, 8 and 4. Okay, so here I want to permit 1 out of 16. So 16 combinations if I want to have, then I should have 4 bits. 4 bits, that is from 0, 0, 0, 0 to 1, 1, 1, 1. Okay, so with this combination I can have this, I can have as your 16 combinations. 16 combinations. Okay, now with this 16 combinations I can select one. If I send 0, 0, 0, 0, I will get the first combination. If I send 0, 0, 0, 1, I will get the second combination. If I send 0, 0, 1, 0, I will get the third combination. So I require 4 bits. So the number of bits required are 4. So here the option should be option D, 4 bits. So to permit the selection of 1 out of 16 equiprobable events, the number of bits required is 4. Okay. Then we'll go to question number 19. The Shannon-Hartley law refers to distortion, defines bandwidth, describes signaling rates, refers to noise. Okay. Now here Shannon-Hartley is giving you an expression where channel capacity is equal to bandwidth into log 2 into 1 plus s upon n, signal upon noise. That means it is going to describe your signaling rate, how much rate you can send, how many bits per second you can send on the channel. So option C will be the correct one. The Shannon-Hartley law describes the signaling rate. Okay. Then we'll go to question number 20. A forward error. This question is on error correction and detection. A forward error correcting code corrects error by. Okay. So the options are requiring partial retransmission of the signal, requiring retransmission of the entire signal, requiring no part of the signal to be retransmitted, or using parity to correct the errors in all cases. Now if you remember the forward error correcting system, now there we have said with an example that if you use a parity type of generation, okay, and in the receiver part, when the data is received, if you see any error is occurred, error position is known in that case, and if any error is occurred, if 1 has become 0 or 0 has become 1, you have to just invert that bit. 1 should be made 0 or 0 should be made 1. That means this type of technique doesn't require any signal to be retransmitted. It will find the location of the error at the receiver and it will revert that bit and it will rectify the error. Okay, so option C should be correct here, requiring no part of the signal to be retransmitted. So the forward error correcting code corrects the error by requiring no part of the signal to be retransmitted. Okay, so these were some of the first 20 questions on digital communication subject which I have taken today. Okay, so if you have any problems in this, any doubts in this, you can call me and ask me, or you can send me a message. Okay, but see that all your basics of digital communications are very clear. You can start your study from what is a signal, what is a noise, how do a signal represent, what are the types of signal, okay, then what is your analog quantity, how do you convert that analog quantity into digital quantity, okay, and then how that digital quantity means what is sampling and quantization. Then to do this sampling and quantization or to convert analog to digital, what are the basic modulation processes you're using, that is pulse code modulation or differential pulse code modulation or delta modulation, adaptive delta modulation. These are the modulation techniques what you use to convert analog signal to digital signal. So those concepts of PCM, DPCM, DM and ADM should be very clear to you. Okay, and apart from that, definitions like entropy, information rate, Hartley theorem, Shannon-Hartley theorem, okay, all those things should be your clear, so that based on that you can solve any type of objective type of questions, any type of MCQs. Clear? Thank you, students.